everybody. Okay, so continuing on our discussion about the relationship between distributed load, shear force, and bending moment, but the calculus relationship. Let's try this example here. So first we want to solve for the reactions at this fixed support. So this is a fixed support. Fixed support meaning there's got to be a force and a couple. Okay, so this is point A, so I'll decompose this into X and Y and then some couple. And there's the distributed load here, but I will represent this distributed load as a single force, which is the area of the shape. So 1/2 base times height would be 900, located at the centroid of the shape. So here to here would be 2/3 of 6, so 4 meters. Here to here is 1/3 of 6, so 2 meters. Okay, now let's solve for these reactions. Okay, so in the x direction we have ax, the y direction, ay minus 900, in the sum torque. So let me sum torque about over here, about point A. Okay, so then there's no torque from AX or AY, but there is torque from this 900 Newton load, which is 4 meters that way, so minus 4 meters times 900, and then there's this reaction over here. Okay, so AX is 0, AY is 900, and the couple MA is 3600. Okay, so it looks like AY is 900. Let me draw it over here. I'll draw it over here. AX is 0. There's a couple 3600 Newton meters. And the distributed load. Okay, now what is this loading curve? Okay, so it's a function. It's linear. And then what is the slope? Rise over run. So 50 x, and then the y-intercept is 0. So this is the loading curve as a function of x. Okay, now let's solve for the shear and bending moment, but using the calculus way, where we know that dv dx is minus w. So let's give it a try. Okay, so if you're moving along, if you're cutting the beam over here, there's no shear anywhere, right? We're not even at the beam, so it's definitely 0 over here. But then suddenly we encounter this 900 Newton reaction going upwards. And then is upwards positive or negative, right? If we're cutting the beam this way, when we cut it like this, it exposes the axial force, shear, and bending moment. Okay, so upwards, it would be positive. So that means suddenly we encounter this 900 Newton shear, which is positive. So it goes upwards over here, where this is 900. Okay, and then what happens between here and here? There's this distributed load, which is 50x. So it's minus W, which is 50x. Okay, so how do we solve for shear? Just let's move dx on this side and then integrate both sides from x equals 0 to some other x between 0 and 6. So this is between 0 and 6. So this is v at 0 to some other v. So what do we have? Minus 50x squared over 2. Let me just write that as 25. Okay, and what was V at 0? 900. So let me just put that number in there. Okay, so here we go. That's the shear. What does that look like? So it's a parabola, right? And then see the leading coefficient is negative, so it's definitely this kind of shaped parabola. And then at x equal to 0, it's 900. And then as you increase x, what happens? Like if x equals 1, 900 minus 25, x equal 2, 800. So it's decreasing. So it's this side of the parabola, not this side. So it's going to look something like concave down. And then what happens at x equal to 6? 6 squared times 25 is 900, so 0. So this goes down to 0 over here. There. Okay, so this is the shear. Okay, hopefully not too bad. Just practice doing this method. How about the bending moment? Okay, so bending moment. So over here in the middle of nowhere, there's definitely nothing, right? So it's 0 over here. But then suddenly we encounter this couple, which is going counterclockwise. And then again, which way is that, right? Axial force, shear, bending moment. So bending moment is positive this way if we're cutting it over here, but this couple is going the other way. So it's actually negative 3600 like this. So this would be negative 3600. Suddenly, because of this couple. Okay, and then what happens between here and here? There's shear that looks like this, that looks like this. So how do you solve for the bending moment? dm dx equals v. Okay, and then v in this example between 0 and 6 meters is 900 minus 25x squared. So how do you solve for bending moment? Move dx over here and then integrate both sides. From 0 to some other x between 0 and 6. Okay, so what do we have? M minus m at 0, which in this example is negative 3600. And then just integrate this, 900x minus 25x cubed over 3 from 0 to x. So just like this. Okay, and then I can move this on the other side of the equation. So then we have here we go. Okay, and what does that look like? At x equal to 0, it's negative 3600. And then as you increase, so let's say x equals 1 minus 3600 plus 900 minus 25 over 3. So it got larger, so it's on its way up this way. And then as you increase x, it continues to increase. And then at x equal to 6, you plug that number in, this whole thing becomes 0. So it's increasing and then reaches 0 over here at x equal to 6. Okay? All right, so keep on practicing this calculus method. It's straightforward because there are only the two equations for shear and then for bending moment. Right, it's only these two. Those are the only two formulas I used. Straightforward, but just keep practicing till you get the hang of it. And there's also the method where you just cut it right? And then take the section. So you want to practice that method as well, but definitely spend some time practicing these calculus relationships because there's more to the story in future semesters. So, because if we take this bending moment diagram, integrate one more time, you get something called slope. You integrate that slope one more time, you have something called deflection. And so the function of the deflection is literally the shape of the beam as it's deflecting under load. Okay, so let me know if you have questions, and I'll see you in the next video.